Hello everyone. So it's me again. It's been a really long time since I have made any video for YouTube, and till now, I guess I have been making videos only on gameplays. As you can see, it's been more than 3 months since I have uploaded any video on YouTube. Today, I'm going to change that. So what is happening is I've been working on segmentation models since a long time. So I thought that maybe today I'll talk about it. So we will go to the segmentation models website. This is a model made for segmentation purpose. This model was made by Facebook Research. So if you look here, this model basically does segmentation based on point prompts, box prompts, or mask prompts as well. Although it also works for text prompts, but in the repository they have not released the code for the text prompts. So unfortunately, we will have to look only on the point prompts, box prompts, and mask prompts. So if you want to learn more about this, then you can just visit their website, segmentation.com, and you can try it out. You can learn about the dataset on which the model was performed, trained, and all. Right, so we will look at the demo. So if you look here, we have one image and we have hover and click type of prompt. So basically when we hover over the object, it will show us the segmentation in real time. And when we click, then based on the click prompt, those are basically the point prompts, it will give us some kind of segmentation. Right. So as you can see here, with this point prompt, it is giving us this segmentation. Apart from this, there is also a functionality of remove area. So these are basically the negative prompts. So when we give a negative prompt, the model tries to understand what area we want to remove. For example, here it understand that okay, maybe we want to remove the tail of the dog, right? But as we can see, it's also skipping the ears, right? So we can give additional prompt by using add mask, and based on these additional prompts, the model will again be evaluate, and it will show us some new segmentation. But from this prompt, we can give box prompts as well. As you can see here, when we give a box around the object, the model automatically gives us the segmentation for the dog. If we give a prompt only around the tail, if we give a prompt only around its waist, it will give us segmentation. But of course, there is some kind of segmentation as well. Apart from this, there is one everything option doing this. The model will automatically segment everything inside the image. So it will divide the image into multiple parts where there is some grass, and then we have the dog, we have the collar, and there are trees and all. Right. So now we will go to its repo, and we will try to install it on our system, and then we will see. We just copy the link, and then I'll just quickly open the CMD. I'll install it in the C directory. This will just to git clone and oops. Right. Okay. Oh, right. So this ls command does not work on CMD. So we have to use the. All right. So I'll try to open VS Code. So basically, in the segment anything repo, we have one segment anything folder. So this is where our actual code is related to the model diagrams and all, and model architecture and all. So this is what we are interested into. There is one file called buildsam.py. Inside this file, we have the utility to build a SAM model with different types of backgrounds like Vit-H, Vit-L, Vit-B, or I mean, yeah, these types. And they have also provided some code for prediction. But as for now, I think we can skip this. Now, let me just check if the torch installation is done or not. So we do this quick test, and then yeah, there's torch 2.4.1, torch already 2.4.1. But let me check if this is enabled for code operations or not. So I'll just open Python. I'll just import torch. Taking quite some time. Right, so this is enabled for CUDA operation. So I think we are good to go. Alright, so here we can, let me see if predictor.py uses buildsam or not. So it does not use buildsam. It's okay, we can skip this. So in buildsam.py, we basically create a SAM following this function. So we are building Vit-H. So in Vit-H, we if we are not passing any checkpoint, then it will it will generate a Vit-H based SAM with some randomly initialized weights, and then we basically call build SAM, inside which we pass several parameters such as encoder embed dimension, encoder depth, or encoder number of heads, encoder global attention indexes. I'll later talk about what this means, and then of course the checkpoint that we are not using. So for Vit-H, the encoder embed dimension is 1280. The encoder depth is 32. That is different for Vit-L or Vit-B. In case of Vit-L, this is 24. Vit-B 12. And the number of heads in Vit-H is 16. So this later on basically affects the calculations. And we have the global attention indexes. I'll later talk about what these are. So first of all, we have this image embedding size. So this is basically our image size divided by VIT patch size. So by patch size, we mean basically the size of kernel. So this image encoder divides our original image into multiple subparts, right? So since our image size is 1024 and VIT patch size is 16, in this case, our image embedding size would be 64, right? So we use a convolutional layer that will operate on your input image, and it will transform its spatial dimensionality from 1024 cross 1024 to 64 cross 64. So now we look into the SAM. So SAM basically expects these things: image encoder, then we have the prompt encoder, then we have the mask decoder, right? And of course some other things like pixel mean, pixel standard deviation, these kind of things. So first of all, we will look into the image encoder. So we go inside this image encoder PIP. So just so you follow, basically to go inside this, what you do is you press CTRL and then you click through your mouse, and it will take you to the function that is basically there, right? So this image encoder VIT class, this will basically generate your image encoder of SAM. So in this we have the image size, patch size, and other things such as your input channels, then the image embed dimensions. So this embed dimension will be different for your Vit-H. This 768 is basically for Vit-B. So for Vit-H, this is basically 1280, I think. Let me just verify. Yeah, so for Vit-H, this is 1280. And this depth is, I think this depth is also different for Vit-H and Vit-B. So this embed dimension is 1280. The depth is 32. The number of heads is 16. And the rest of the things are same. So we have the query key bias that will affect our query key value layer in your attention head. Then we have whether we want to use the absolute positioning or not. And then a relative positioning should be initialized with 0 or not. And then we have the window size and global attention index, right? So we just initialize the image size, and then we have the patch embed. So this patch embed is basically a layer that will transform your input image into some initial tensors that will get operated on by the blocks. So this kernel size will basically be 16 cross 16 because your patch size is 64 Vit-H. This stride will be also 16 cross 16. The input channels will be 3, and the embedding dimension is basically 1280. Now we look into this patch embed. So this patch embed will basically have one 2D layer. So this con 2D layer will be used as a projection layer that will have in channels as 3, the embed dimension as 1280, the kernel size will be 16, and the stride will be 16 as well. So the output shape will be basically 64 cross 64 cross 1280. 64 because your image size is 1024 and your patch size is 16 with stride of 16. So it will get divided and then it will give you 64. So I think while we are going through this code, I think I should start drawing the architecture as well so that we have a clear understanding. So let's suppose this is our patch embed layer. Let's give it a color like this. The input to this layer would be, we also give the batch information. Oh damn. So if we also give the batch information, then input would be b cross 3 cross 1024 cross 1024. Right. So this is your input, and the output from your patch embed would be something like this: b cross 1280 cross 64 cross 64. I hope you understand why this is 64 cross 64. That is basically because in our patch embed we have a 2D convolution layer with a stride of 16 cross 16 with a stride of 16 and with the kernel size of 16. So it will move across 16 cross 16. So this is basically 16 cross 16, and each time it will move horizontally and vertically 16 species. Right. Now if you go back to our code, now this part is done. Now we are basically checking whether we are also using absolute positioning or not, right? And since for us this is true, so what will happen is it will create a parameter layer which would be randomized and which will have a shape of 1 cross 64 cross 64 cross 1280. Right. So let's just go and draw that as well. Let's say this is it. So let's say this is the output of our patch embed layer. Right. And let's say this is basically our random position embedding with shape of 1 cross 64 cross 64 cross 1280. Right. Now that this is done, we will create a module list. So this blocks will basically hold our actual blocks of the image encoder, and for the Vit-H we have a depth of 32. Right. So this loop will run for 32 times, and each time this loop is executed, one block will get formed and it will get appended to our module list. Right. Now one would wonder what is the difference between one block and other block. Right. So as you can see, all of these parameters remains same except our window size and input size. Right. So what this says is, if I is not in the global attention indexes, that is the current block that is undergoing the process is not in the global attention indexes, then it will use the window size, otherwise it will use 0. That means if your let's say if I is 0, which is not in global attention index, then it will use window size, that is 14. And if I is in global attention box, let's say I is equal to 7, that would mean window size is equal to 0. Right. And similarly here basically what will happen is your input size right, input size remains the same, so the only change is in the window size. Your input size is basically what, 64 cross 64, because image size is 1024 and patch size is 16, so this will be 64 cross 64. Now so what is the actual difference that this parameter makes? To understand that, we will go through this block. Right. So inside this block, what happens is this normalization layer, second normalization layer, these remains the same. This window size varies depending on whether this is attention block or non-attention block. So this will either be 14 or 0. Right. And this MLP block is it also remains the same, right? Because our this MLP ratio is 4 and dimension always remains the same. Right. So this dimension is 1280, number of heads is 16, MLP ratio is 4. This is true. So basically this QKB bias, it tells whether inside our query key and value layer we want to use the bias or not. That's all. This normalization here, I'll just skip this. And relative positioning, this is for us, this is false, right? So this is false. And relative positioning, zero initialization, that is true, right? Now, so inside this block, we know there are two types of blocks here. Two types, depending on what, whether we are using attention block or normal block, right? Now, sorry, not, yeah, whether we are using global attention blocks or normal attention block, right? So if it's a normal attention block, so inside this, what is passing is basically 1280, 16. This is true. This is false. This is true. And here, the change comes. That is whether we are using global attention block or normal attention block. Here it will get reflected. So if the window size is 0, that means we are using what? See, if the window size is 0, that means we are using a global index, global attention index. So that means our input size will remain 64 cross 64. Otherwise, if the window size is not 0, that means if there is some window size, then it will use input size of 14 cross 14, basically because our window size is 14, right? And then afterwards we have a normalization layer, then we have a MLP block, and so on, right? So basically this is what will happen. The input potential will produce 3 times more channels going by this linear layer, and then we have a projection layer that will have the same input dimension and the output dimension, because this is just a projection layer, right? And if we are using a relative positioning, that is false for us, then we do not really have to worry about this. So let's just skip this for now. Now similarly, non-2 layer will be formed, and then MLP block. So this is basically our multi-layer perceptron block. So this will be formed. So what happens inside this multi-layer perceptron block is you have 2 linear layers, where the first linear layer will have a input dimension of 1280, and the MLP dimension, that would be your basically the output dimension, that is basically 4, right? That is sorry, MLP dimension would be dimension multiplied by MLP ratio, that is 1280 multiplied by 4, right? So where did it go? Here you will have 1280 multiplied by 4, right? And then here you will have 1280 multiplied by 4, and then output dimension is 1280, right? So that is what happens inside the MLP block, and then this is just a window size. So this is how your one block is formed. And now since we know what happens when I is equal to 0, so now we will see what happens when I is sum of the global attention indexes. So we go inside this block, and these values are changed, right? So these input size of your attention block will become 14 cross 14. Sorry, for global attention indexes, the input size will become 64 cross 64, and that will basically affect during the forward pass. That is why I think right now it's not really clear, but when we look in the forward pass, it will make more sense, right? So similarly, all of the blocks is processed, and we form a module list of all of the blocks, and then we go to the neck. So in the neck, what happens is we have a convolution layer where the input size is 1280, and output channels is basically whatever we are passing to it, right? So as you can see, where is it? Yeah, so output channel is 256, right? So from this convolution layer, we will get a output channel of 256, and then again we are passing that to a normalization layer, and then again to a convolution layer, and again to a normalization layer, and that is basically whatever neck is giving us, right? So now that we are past this, we will go into the forward pass so that we have a better understanding, right? So as we can see, this is your x is basically 3 cross 1024 cross 1024, right? And that is sent to our patch embed, and our patch embed generates something like b cross 1280 cross 64 cross 64, right? And then we check whether position embedding is true or not. So in our case, position embedding is enabled, right? So this x will get added to our position embedding. Now there's one more thing inside this patch embed. So when we are doing forward pass, so apart from passing it to the projection layer, it also changes, it also does some permutation on it. So this batch channel height width gets changed to batch height width and channel. So this will get changed. So this will get changed to something else. Let's do one thing. Let's just copy it again, and copy this again as well. So this will get changed to batch height height, width, and channel, right? Let's just add something like this, right? And then, so basically this is finally what is returned from the patch image layer. Now we will go again back to the forward pass of our image encoder, right? So in our case, this positional embedding is enabled, so this X will get summed with our positional embedding, which is this. Now we can see that the channels are matching. We can actually add them. So it got added, and then we got something that will remain same as this one. Addition. Alright, this will work. So both of them got added, and we got something. Right now, this X will get passed through all of the blocks, right? So by all of the blocks, what we do is we keep this block 0 here, and let's move them. So this X will go to our block 0, and what will happen inside block 0, I think I can show you. Alright, so I'll do one thing. I'll show for block 0, and you guys can understand for a block from block 0 to block 6. And I'll again show for block 7, and then of course you guys will know what happens inside the non-global index blocks and global index blocks, right? So let's just move them. And inside block 0, what happens, right? So inside block, when we do forward pass, so what happens is basically so this is just a variable for it. We pass the X with a normalization layer. So to represent a normalization layer, what I'll do is let's use this one. So let's say this is our normalization layer, norm, and let's give it some bad color like this. Nah, like this, yeah. So this is our normalization layer, and the shape will remain same, right? So this is the input, and this is the output. Shape won't change. Let's also denote the arrows as well. So this is not right. Now after this, what happens is, see, if self dot window size is greater than 0, and we know that for global attention index, window size is 0, otherwise window size is 14, right? So for our 0th block, this is 14. That would mean this if condition is true. So what happens is we will do window partitioning. So first of all, we will extract this H and W. So this H and W are basically 64 and 64. Now this X will go to our window partition, and we will also pass window size. Window size is basically 14. Window size is 14, right? So we will go to the window partition function. So inside this, what happens is we extract the batch height, width, and channel. So batch is basically B. These are 64, 64, and 1280, right? And then we find out how much padding we need to do, right? So here basically what happens is our window size is 14, window 14 minus height divided by window size. So our height is 64. So 64 mod 14, what is it? Basically 8, right? And this is again modded by 14. So what it gives us is 6, right? So similarly, our padding for the width will also come out to be 6, right? So now if our pad height or pad width is greater than 0, then what happens is it will pad those values to our X, right? So now what this will basically do is, so basically what happens is the shape of X here will become something like B 70 70 and 1280, right? So basically we are passing the X, and then we are passing the values that we want to pad. So this pad W would be on the right side, and then on the bottom side. Now we find out HP and WP. So this is basically 70 and 70. Now we change the view of our X. So it basically becomes what? Becomes our B, and HP divided by 14, that is basically 5, and then window size, that is basically 14, and WP divided by window size, that is again 5, and then 14, and then 1280, right? Then from here we are returning our windows, that is basically this thing, along with our 70 cross 70, the new padded height and width, right? So this happens inside your window partition. So I think I do not really need to show this here, but let's see if I can. So here, or maybe I'll just leave it. So this goes inside window partition, and from window partition we get some things. That is basically 25B and 14 20 80 along with 70 70, right? So this is what we get out of our window partition function. Now we go back to our block, which is here, right? So here x becomes this. Oh shit. X becomes 25b cross 14 comma 14 this, and the remaining thing 20 comma 20, right? And then this thing is passed to our attention block. So now for this attention block, we know that we got it from this attention here, right? So we will go to this attention and then we will look for the forward pass. So here we will get 25b as the batch and 14 14. We are not interested about channel, but let's say it's 2080, right? So now what will happen is we will pass this x to our QKB, and then we will reshape that, right? So if we pass that to our QKB, we know that it will generate three times our input channel. So initially that will give us 25b cross 25b cross 14 cross 14 and cross let's just say calculator, and 1280 cross 3, that comes out to be 3840, right? So this will be 3840, right? So now this will get reshaped, and we are basically reshaping it to Vit-H cross W and 3 and so on. So B would be 25b, H into W would be 196. Self-dot number of heads. Yeah, so basically here where the number of heads comes into. So basically we are dividing this tensor into sub-tensors of this shape. So since we have 3840 and we are dividing that into 16 into something, so that would come out to be 16 into let's just calculate this divided by 16. So that is right, I missed this 3 as well. So here it would be 3 and then 16, and 240 by 3 is basically 80, right? So this is what we get from here, and then again this will be permuted. So finally what we will get is 3 cross what we will get is 3 cross 25b cross 16 cross 196 cross 80, right? So basically this QKB will be 3 cross 25b cross 16 cross 196 cross 80, and then we are basically unbinding that. But before that we again do reshaping, right? So when we do reshaping of that, what we will get is 3 cross b into self number of heads. So that is basically our 25b into 16 and cross 196 cross whatever remains. That is basically our we got 3, we got 25b into 16, we got this, so here it will become 80. So that would basically lead us to what? That will be 3 cross 400b cross 196 cross 80, and then we are unbinding this across the 0th dimension. So this will result into each of these QKB becoming 1 cross 400b cross 196 cross 80, right? Or basically each of these QKB becoming this. And then here what we do is we apply the self-dot scale to our query, and then we do matrix multiplication with key, and of course we have to transpose the key. So this q will get multiplied with 0.118, as we found out that our scale is 0.118, right? And then we will do a matrix multiplication with a shape of we are doing k dot transpose minus 2 minus 1, so that would basically mean 400b comma 80 comma 196. So this would result into, so basically what is happening here is we are multiplying two shapes, right? First shape is 400b comma 196 comma 80, and the other shape is what? 400b comma 80 comma 196. So this would result into a shape of 400b comma 196 comma 196, right? And then we determine whether we are using relative positioning or not, right? So since we are not using relative positioning, so we will just skip that, right? So this add decomposed relative positioning will not get executed. We will pass this attention to our softmax. So this attention shape will remain 400b comma 196 comma 196, and then again we are doing a matrix multiplication of this attention with our v, right? That would mean we are basically multiplying 400b comma 196 comma 196 with a shape of 400b comma 196 comma 80, right? That will basically give us a shape of 400b cross 196 cross 80, right? And then we are again using v on this, so this will basically give us here, since b is our 25, so it will come out to be 25b, number of heads in section, so this will become 16, and then height and width, those are basically 14 and 14, and whatever remains, so what remains is 80, right? Because this was 400, this is 196, and the remaining 80, and then again we are doing permute, so it will give us a shape of 25b comma 14 comma 14 comma 16 comma 80, right? And then again we are using a reshape, so it will give us 25b comma 14 comma 14 comma 1280, right? Now so now this tensor will again go through the projection layer, and as we saw that inside the projection layer the output dimension will remain same, so even after doing the projection we will get the same shape, that is 25b comma 14 comma 14 comma 1280, right? And this will finally get returned, so we will get back to our this block. So here x will have a shape of 25b comma 14 comma 14 comma 1280 in case of non global attention index block, right? And then since we are using a window size here, so we will have to do window unpartition. So what happens inside this is we will get back our original shape, because we had added some padding, right, when we were doing a window partition. So we will go to this all right, so before going to the window partition, I think I will draw the block for the attention block, right? So how do I do it? Right, so inside the attention block we had a QKB layer, so I'll just draw it here. Let's keep this as the bigger block, send this to back, and let's add something here. Since I have to add a linear layer, I'll just make it like this. So this is our linear layer that will have this as the input, right? And the output for this would be 25b cross 14 cross 14 cross 3840, because we are basically getting 3 times more channel in the output, right? And I think I can show the operations as well. Let's do one thing, let's rotate this here like this, right? So after doing this, what we did is we did some operations on this tensor, and then we divided this, right? So how do I do it? Let's do one thing. I will use this block. So basically we got 3 of them, right? So we got 3 of them. Let's say this is Q, this is key, and this is V, right? Let's get this color. Okay, so QKV. So we are basically passed here. Now we get the attention tensor using Q and multiply it with the scale, and then we do K transpose. So I think I won't show the transpose operation, because that is that is trivial, right? So we get a right. I think I should write the shapes as well. So this was 400b cross 196 cross 80. Similarly this and similarly this. So we got our QKV, and then we get our attention. So let's just use this one for attention, and the attention is obtained by multiplying Q with our K dot transpose. So it should go here, and I'll just use this one. So basically for matrix multiplication, I'll use just some multiplication. Okay, so there is no sign for multiplication. Okay, I'll use this one. So we pass Q and K, and we also multiply this Q with 0.118, right? So I'll just denote that somewhere around here, 0.11. 8 times. This will give us our attention. Right. Now we got our attention, and the shape of this attention is the shape of this attention would become what? 400B, 196, and 196. I think I should have also added the depth visualization. It's fine. I think I'll just make this a little bit bigger. Right. So now I got my attention, and then we just apply softmax to this. So I'll just do one thing. I'll write attention to softmax. Right. And then this will participate into a matrix multiplication with our value. That is our V. Let's pass it here. And right. So this attention plus softmax will participate into a matrix multiplication with our value. And then of course we again do some kind of operations on it, and we get some tensor with the shape of what? With the shape of 25B, 14, 14, 1280. So that is basically our input shape. So I will just use something like this. All right. So I'll call this what? Let's just call it not attention. Let's call it X. Right. So this is our X. After some operations, and this will give us a shape of what? 25B cross 14 cross 14 cross 1280, and then again this will go to a projection layer, right? So I'll just remove this, and I'll use this one again. Projection. And this will give us same shape again, because there is no change in the number of channels. So this is what we get from our attention thing. After all right, so now that this is done, this is done, I'll have to implement this window unpartition. So basically what happens in this window unpartition is we get the pad HW and sorry, pad height and width. So that is basically 70 and 70, right? Right. Pad HW, that is 70, 70, original height and width, and the X and window size. Right. So this original height and width would be 64 cross 64. This would be 64 and 64, and then windows dot shape 0, 25B, right? And this would get divided with our HP into WP. So HP into WP would basically mean 70, 70, and then we have the window size, that is 14, right? And then again 14. So that would basically mean we have 25B and 5 into 5, right? So that would basically mean this B is 1, and then this X, basically what we are doing is we are changing the view to 1 comma 70 divided by 14, that is 5, and comma again 5, and then 14 and 14, and then what? So our windows should have been what? Our windows should have been 25B comma 14 comma 14 comma 1280, right? So this changes it to 1 5 5, and then 14 14. So what do we need? We have 1280, right? And then we use permute, contiguous, and then view. So basically what it does is 1 comma 5 comma 14 comma 5 comma 14 comma 1280, and then it will change that to 1 comma 70 comma 70 comma 1280. And since this is greater than our H or W, so our H is, these are basically 64 and 64, right? So basically here we are taking out 1 and 64 64 and 1280, right? So this X is basically 1 64 64 1280, or let's just say B. right? Instead of using 1, let's use B everywhere, right? So basically that is what the Windows unpartition does. Now we are back to here. I'll add window unpartition. I think I should give some color to these as well. All right, so when we do window unpartition, now what we get is something like this. So this will go back to B cross 64 cross 64 cross 1280. Right. So here we have B cross 64 cross 64 cross 1280, and then we are using the subtraction, right? So here they took a shortcut very well, but we do not really need to do it. We can, okay, so this shortcut was made for normalization, right? So what we can do is I'll just add a connector like this, right? So let's just add it here after partitioning, right? So it will get connected there, and then after we are done doing this, then we pass that to another normalization layer and then to the MLP, right? So what that means is we will just copy this normalization layer somewhere around here, and let's move it to a little bit left so that I do not have to make another arrow, and then this will go to our normalization layer. It will produce something that will go to our MLP layer. MLP. This MLP layer is pretty much straightforward. Right, and then again this X is added to it, right? So that X meaning this one before the normalization layer and after the normalization layer. Okay, I think I should do it after, no. Right, in the output of our MLP. Okay, so I think I should also show the MLP as well so that there's no confusion. So what happens in the MLP is it is basically consisting of two linear layers. Right, so this should be pretty straightforward to make. I'll just do one thing. I'll make something like this, send it to back. Then I need two linear layers, right? Let's copy this one. Okay, two linear layers. The input is the emitting dimension, and then the output is MLP dimension, that is 1280 into 4, right? So basically, I'll show it with this arrow. So this is the input. The output of first one is 1280 into 4. That would mean 1280 into 4 is 5120, 5120, and this goes as the input to the second one, and this should be the final output. Let's just check again. Yeah. That's good. I hope so. Right. So basically, this is the output, and it has the same shape. So this will have a shape of this B6464 to LED. Now, so all of this is block 0. Okay. Similarly, we have from block 0, we have block 1, we have block 2, and so on. So the output of each of these blocks, that is this final output B64, 64, 1280, that goes into the next block, right? So if I just show it here, so it would be something like this, and then it would be something like this. Now I'm not going to show some of the further blocks because they are basically doing the same operations, right? But now I'll show the block number 7 of the global attention index blocks, and let's make it in this color. Right. So now there's not much of difference apart from let's do one thing. I'll first group them together, and then I'll just copy them, and then I will ungroup them. So the difference is, first I'll show you through the code. So the difference is, right, so when I is 7, that is in the forward pass, when we are using the 8th block, or let's just say the very first global attention index block. So what happens is, it will go inside the forward pass of your block. Similarly, it will apply the normal addition layer like we apply in the normal blocks, and then here the difference will come. Since the window size is not greater than 0, so there is no window partitioning. It will directly go to your attention layer, right? So that means this thing will not come. It will directly go to the attention layer, and even inside this, the shape of the tensors will get changed. How? I'll show you. Like if we go to the attention one, and if we look at the forward pass, these things will remain same, but what will change is what will change is when the attention layer of this particular global attention block was getting formed. So this number of head was 16. These things remains same, but what changes is B, right? So how does it change, you would ask? So it changes because when you were doing a window partition, so in window partition, see, this was B and you had 64, 64, but after partitioning, you got 25B, right? And basically, this tensor got partitioned into multiple windows, each of size 14 cross 14. But right now, there's no partitioning, so the B remains same, and these tensors are not partitioned into windows of shape this, but remain same as 64 cross 64, right? So, right. So what happens is here when you pass the tensor, this x dot shape will return something like 4 global attention index blocks. It's B cross 64 cross 64 cross 1280, right? So that would mean all of these shapes will get changed. This won't be the same, right? So I'll do one thing after this. Whatever I write would be in context of global attention blocks, right? So here what will happen is instead of after passing this x to QKB, instead of this tensor, what we will get is we will get B cross 4096 sorry, B cross 64 cross 64 cross 3840, and then it will get reshaped to B cross 4096 cross 3 cross 16 cross 80, and then it will get permuted to something like 3 cross B cross 16 cross 4096 cross 80, right? And then again here, what it will give us after reshaping is something like 3 cross B into 16, right, cross 4096 cross 80. That will lead us to 3 cross something like 16B cross 4096 cross 80, right? That would mean our QKB are now 16B cross 4096 cross 80 instead of 400B cross 196 cross 80, right? So that is the difference it makes. And similarly, all of these values will get changed, because basically here instead of whatever was before, what will come is something like 16B cross 4096 cross 4096, right? This would be the shape of attention. And since this is false, so let's not bother about it. So this will become 16B 4096 and 4096, and similarly this will change to something else. And here, after applying attention and we get a shape of something like B cross 64 cross 64 cross 1280, right? And then we just pass it through the projection layer. Okay, so this would be B cross 64 cross 1280, and we just return it. So basically, that is the only difference between the attention layer and the global attention index layers. Afterwards, all the other steps are same. We apply the normalization layer and then we pass it to the multi-layer perceptron block. And here basically the window size will remain 0. And of course, since in the global attention indexes there is no window partitioning, so there won't be any window partition as well. We just apply the skip connections and then the normalization layer, MLP, and again the skip connection. So if we look at this, basically these two will go away. That will go away, and this will go away. Wait, this window unpartition will go away, and this block basically shape will also remain the same, right? I want to ungroup this, but I don't know why it's not giving me the option. Yeah, right, ungroup, cool. So now I'll just move this a little bit left side, and do these as well, or I'll just delete this and move one of this to left side. Right, and of course I have to make changes in these accordingly. So this should be 16B cross 64 cross 64 cross 3840, right? Sorry, not 16B, just B, and here it will be 16B cross 4096 cross 80, and I'll just copy it, and here it would be 16B cross 4096 cross 4096. Here it would be B cross 64 cross 64 cross 1280, and similarly here B cross 64 cross 64 cross 1280. Right. And similarly we will apply other blocks as well till block number 31. Okay, so 31 is also a global attention index block, so I should copy this one, right? So sorry, I'll group them together. So after processing all of these blocks, as we saw in the forward pass of our image encoder, so after the blocks are processed, we process the neck, but before processing the neck we permute it. So basically at first the tensor was having a shape of this, which will become what? Which will become B cross 1280 cross 64 cross 64, and then this will go inside your neck, and your neck is basically having two convolution layers and two normalization layers, right? So basically what I will do is, since it's just about convolution layer, I'll just copy this one, right? So this would be our conv1, conv2d. It will have k as 1 and bias is false, right? As we can see here, the bias is false in both of these convolution layers. Kernel size is 1 and input dimension is 1280 and output dimension is 256, right? So here what will happen is, basically this would be the shape that we will be getting out of our block 31, and then after our conv2d, what we will get is something like this: B 256 and then 64 and 64. Of course, since we are changing the dimension, then I'll do one thing. I'll change it here. So this is what is going inside your block 2D. This is the output of your block 31. Then we are applying a normalization here. which will keep the dimension at same. And then again we are applying a conv layer, but this time the kernel size is different and we are using padding, right? So this time kernel is 3, bias is still false, and then again we are applying a normalization layer, which will give us our final output of the image encoder. That is something like this. That is basically our image embeddings. So our image embeddings will have a shape of P256 64 cross 64. Right. So this is the whole workflow of the image encoder. Right. Cool. So this would be the whole architecture of the image encoder of our segment anything model with our Vit-H backbone.